about bipolar junction transistors. This is chapter 9 in the book. We know that it's a current valve, right? Everybody understand it? Transistors are current valves. We know we have two categories. We have bipolar junction transistors and FETs. We'll try to touch on FETs just a little bit, but unfortunately we don't have a lot of time when we come back. We looked at how they're constructed. We know about NPN, PNP. Everybody okay? So NPN is predominantly what we use on a positive power supply, and a PNP is what we use predominantly on a negative power supply. And we talked about the different units. We understand the symbols now, right? Talked about bias. We know bias is DC levels that sets the operating parameters of a solid state device. Reverse bias, forward bias. So to make the transistor work, to make the bipolar junction transistor work, we forward bias the basic emitter, and we reverse bias the basic collector, right? Everybody okay on that? We talked about the way it works. The biggest current in the transistor, we know it's the emitter current followed by the collector current. In fact, the emitter current and collector current are practically equal to each other. And the base current is almost nothing, right? Compared to the other one. Talked about the basic formulas for the current formulas. So IE is equal to IB plus IC. IC is equal to IE minus IB. And IB would be IE minus IC. But we assume that IC, for calculations, we assume that IC and IE are equal. But just for calculations, if you ever say, are they equal, you're going to say no, right? You understand? We talked about the three regions we can operate it: the saturation, cutoff, and active region. And we know we use this voltage collector to emitter to determine where it's operating in. We talked about the beta. This is the IC over IB, and this gives us an indication of the current gain of the transistor. And of course, these are the formulas. DC alpha, we'll get into alpha a little bit when we look at a common collector amplifier. Alpha is not normally given in the data sheets, but beta is given. So this is the primary formula right here. So DC alpha is equal to beta over beta plus 1. What you have to understand, alpha is always less than 1, because look at the formula. It's IC over IE. What's the biggest current in the transistor? IE. So alpha will always be less than 1. We're given beta, so if you take beta and divide it by beta plus 1, you'll always come up and get a number that's less than 1. So that's the way I know that formula. We talked about the different nomenclature used for these different voltages. So these are what we call these voltages relative to circuit common, right? You understand? This is what we call the voltages relative to from lead to lead. And of course, the one on the right is the common, right? So voltage collector to emitter, would put our common on the emitter, and we'd put our, and this is the guy right here determines if the transistor is saturated or if it's cut off or it's in the active region. If it's less than 1, we assume it's saturated. If it's equal to VCC, we say it's in cutoff. And if it's between 1 and VCC, we say it's in the active region. And then we talked about the supply voltages. So how we look up the supply voltages have their own name either: VCC, VBB, and VEE. So this would be a power supply connected to the collector. This would be a power supply connected to the base. And we haven't looked at VE yet because we haven't got into the common collector amplifier. So this would be VBB. This would be VCC, right? Everybody understand that? Let's see. We talked about different ways we can analyze this. This is what y'all doing right now. You're generating what we call the collector characteristic curves in the labs that you're doing right now. We're only doing 3 levels. Usually they do 6. I think we're doing 10 microamps, 50 microamps, and 100 microamps, I think, on that lab. We talked about single power supply bias, and then designing a switch. Now this is where chapter something starts into. Chapter 10. We're going to get into a little more detail in chapter 10. And we're not going to go over all the biases. The only one we're going to concentrate on is something called a voltage divider bias. If you can do this guy, you can figure out all of it. But we got to learn a few terms before we get into amplifiers and before we get into talking about the characteristics of these amplifiers. We have to talk about something called decibels. Y'all know what a decibel is? Most people call this dB. Ever heard of dB? What is it? It's a measurement. But what does it mean? I mean, how do you know what? Huh? Decibels is what they're called, but what's it telling us? Yeah, but what is it? Huh? Yeah, well, basically we use it not only in audio, we use it in all communication systems. So when you get into networking or when you get into fiber optics or anything like that, you're going to talk about dB. So any communication system, any signals, when we start talking about signals, not power, we don't deal with power. Our power supplies don't deal with dB. But when we get into any type of signals, then we're going to deal with decibels, whether they're audio signals or whether they're network signals. So let's look a little bit at dB, and we're going to deal with what something referred to as impedance matching. So the book touches on it just a little bit on, and we'll talk about bandwidth too. We need to understand bandwidth. I know y'all heard of bandwidth, but what in the world does bandwidth mean? I mean, if you don't know what bandwidth means, you just know that the bigger the number is, the better it is. Right? Y'all understand that? But if you don't understand bandwidth, we'll talk a little bit about that. So some of the things before we get into these amplifiers, we're going to talk about bandwidth. So you go out and buy a stereo amplifier. First thing they're going to give you is the bandwidth. What range of frequencies can it amplify? And of course, then we're going to talk about dB. You have to understand dB to understand amplifiers or any type of communication system at all. And of course, something that's very important called impedance matching. And this is what we'll talk about, these different amplifiers having low input impedance, high output impedance, and why each amplifier has a different. Why do we use common collectors to run speakers, and why do we use common emitter as our inputs? And we'll talk about that. So they talk a little bit about bandwidth. They talk about decibels and impedance matching. They throw impedance matching out, but they don't explain it. The first thing we'll look at is we teach this primarily in a page called cable splicing, which is where we learn about building network tables and stuff like that. So the first thing we're going to talk about is what we call gains and attenuations. We need to know the difference between the gains and attenuation. Talk about voltage, current, and power gains. We'll calculate gains, input and output, and we'll look how to convert gains to dB. So what is a gain and what is an attenuation? A gain should be obvious. What is a gain? You get more out than what you put in. And what's an attenuation? You get less out than you put in. So if we get an attenuation, it means we get less out than we put in. If we get a gain, it means we get more out than we put in. And of course, what's a bell and what's a decibel? That's what we're fixing to learn. Gains are calculated as out over in, period. By the way, in formulas, to represent gain in amplifiers, we use A to indicate gain. And then we're going to put a little subscript. We're going to either call it A little b, we're going to call it A little I, or we're going to call it A little p. So what this means, this is a voltage gain. This right here would be a what? Current gain. And this right here, of course, what is important is the power gain. So all our amplifiers, we want them to get a power gain, right? You understand? Now, how will we calculate AV? Well, AV is going to be equal to V out over V in. What's AI going to equal to? I out over I in. And what's AP going to equal to? Well, it's going to be equal to P out over P in. And what unit does gain have? What unit does gain have? Huh? What unit does gain have? It don't have a unit. It's just a multiplier. It's just a ratio. That's all it is. So if I know the gain, of the amplifier, I can say, okay, if it's got a gain of 10, if I put 10 millivolts in, then I multiply it by 10, and it means I get 100 millivolts out. Or I might say, okay, what input do I need to get 100 millivolts out, right? You understand? So we can rearrange this formula. So it's all gains are in over out. If it comes up to be an old number, if it comes up to be a whole number, it's literally a true gain. If it comes up to be a fraction, it's an attenuation. But it's always out over in, right? You understand that? Does that make sense? Gain does not have a unit. If a voltage amplifier has an input of 100 millivolts and an output of 5, what's the gain? Huh? How did you come up with 4.9? Huh? I would take 5 volts and I divide it by 0.1 volt. Gain is out over in. It's out divided by in. Out over in. So what would my gain be? Yeah, my gain would be 50. What is that? What unit is that? It's no unit. It has no unit. It's either a multiplier or it's a divider. That's like you making $15 an hour, and I say, hey, I'm gonna triple your salary. You said, oh, that's great. I'm gonna get a $3 an hour raise. I'd give you raises all the time, right? You understand? Because you don't understand that gain is nothing but a multiplier. That's all it is. It's just a multiplier. Like I'm gonna give you a 30% raise. Well, what are you gonna do? Well, you'll find out what 30% is, and then you add it, right? You multiply that by, okay. Fractional gains means that it is a loss in the system because the output is less than the input. What is the power gain? What is the power gain in a system if the input is 8 watts and the output is 5.6 watts? 6.56, excuse me. Get your calculator out and let me know. Out over in. So my output is 6.56 and my input is 8. So what would be the gain of the amplifier? 0.82? No. 0.82. Not watts. 0.82. You understand? Gain has no unit. It's either a multiple. So okay. If I know it now, if I know it's got a gain of 8.82, I say, okay, what would be the output if I put 6 watts in? Well, you'd say 6 watts times 0.82, and that would give you the output. Gain has no unit. 50 and here's 0.82. We don't say milli, so when we talk about gains, we give the number. Everybody understand that? Unless we use dB. So dB, we use dB like we use engineering notation. If you understand dB, that's all it is. Is a way that we can represent big and large numbers with few digits. Gains are multipliers that have no unit. If you know the gain and the input to the circuit, how can you calculate the output? Well, if we know gain is equal to out over in, then I can just put this thing in my little equation wheel that we got. Gain is equal to out over N. How could we, if I know the gain, how could I solve for the input? I mean, the output. Well, if I know the gain and the input, I multiply them together. Right? You understand? How can I calculate the output? Well, I calculate the input if I know the output? Well, I take the output and divide it by the gain, and that gives me what input's required to get that. An amplifier has a gain of 23. What will be the output of the amplifier if 0.2 volts is placed on its input? Or 20 millivolts. I'm waiting. 4.6. Everybody okay? It's got a gain of 23, right? So we take 0.02 and we multiply it by 23. Are we okay? Four point six is what it'll be. Oh, I'm sorry. I didn't hear that. An amplifier has a gain of 45. An amplifier has a gain of 40. Okay, listen up. An amplifier has a gain of 45. What amplifier input voltage will cause 7.2 volts to be measured on the output? So here we're given the gain, we're given the output. Now we're going to figure out what input's going to be required to get that. Huh? 0.16. Everybody okay? So I code up, so divided is the 0.46 and then 0.16. Everybody okay? 160 millivolts. And we're going to skip over these. So here's our answer. If a signal passes through multiple gains, the gains are multiplied together to come up with the overall gain. So it's just like if my boss tripled my salary and they tripled it again, what would I be making? I'd be making 9 times, right? You understand? So what we do, it says, okay, I've got an amplifier. The output of an amplifier that has a gain of 23 feeds into an amplifier that has a gain of 47, feeds through a conductor that has a gain of 0.7, so it's got a loss, right? What will be the amplifier? What would be the voltage measured at the output of the third amplifier if 0.2 volts is placed on the input? So tell me. So we're going to multiply all the gains together, right? 23 plus 47 plus 0.7, and then I'll multiply that times 0.02, which will be what we're putting on the input. So what do we come up with? Is that true? Everybody got that? I got, so there's our total gain. Our total gain is 756.7, right? And then 15.13. Okay? So the more consecutive gains we have, the more complex the number becomes. The math becomes. So this is the problem we have. So what will be the gain of this system right here? I don't know. I see 90 on the first one. 15 times 6. Oh, I'm sorry. We got a bunch of fractions. What do we got? 24.6357. So the more devices we go through trying to calculate the gain of the system, the more complicated it becomes. Fractional gains creates an output that is less than the input. This is often referred to as attenuation, but some people still call it gain. In power and communication, media attenuation is also defined as the loss of signal over distance. All media has attenuation. What is media, by the way? What is media? No, it's not possible. What is media? We're not talking about the news media. We're just talking about media. What is media? Sort of. It's what information flows through. So what media am I using right now? What media am I using right now? How's my voice getting from you to you? How's my voice getting from here to you? So the media is air. Media is what the information flows through. So I'm creating vibrations. The vibrations are moving through the air. You're picking up the vibrations through the air. So media is not my voice, right? You understand? It's what the information flows through. We'd be dead. We'd all be dead. Yeah, we wouldn't talk. Yeah. You're right. If we didn't have any air, you couldn't talk. You can't talk in a vacuum. Where you can talk, but nobody would hear you. Right? Attenuation is also introduced by splicing and termination, but this is that class. Back to gain. A communication channel consists of multiple devices, has the following gain. And we can figure this out, but what we're going to do is we're looking at why they give everything in dB. So this whole thing would have a gain of 1,105,444.57. That would be the gain. Now, odds are, we probably need to figure out a way we can kind of approximate this, right? You understand that? Figuring gains using this method requires the use of a calculator. What we want to do is we want to have a method that we can get a fairly good idea of the system without using a calculator. So exponents consist of two parts. We have what we call a base and we have what we call an exponent. An exponent indicates the number of times the base is multiplied by itself. What will this number represent? 5 to the 6. Everybody can do that, but that's a pretty big number. Now, I know, if y'all had algebra yet, how do you do math with exponents? So let's say I had 5. Yeah, but it's got to have the same base. So if I've got 5 to the 6, and then I multiply it times 5 to the 3rd, then it's going to be 5 to the 9. But if I come up here and I say 5 to the 6 times 4 to the 3rd, then the first thing I got to do is get everything in the same base. Yeah. So that adds a little more complication. What if everything used the same base? Well, if we had a system that was guaranteed to use the same base, then we could represent numbers with their exponent instead of the base if the base was understood. Y'all understand that? Multiplying exponents, if they got the same base, we can add them together. Are we okay? All right. The Bell. So we got two type of logarithms. We got a common log, and we got what we call a natural log. Thank goodness we don't have to deal with a natural log. Common logs. What is a log? Well, a common log is 10 raised to some exponent. So the log of 10 would be 1. The log of 100 would be 2. The log of 1,000 would be 3. You understand that? All a common log is 10. That's the base. So a common log, 10 is always the base. Now natural logs, it's 2.735 something. So it's a weird guy. So we're not going to deal with natural logs. We deal with not natural logs for different other things that varies with curves. It's real. But what we're dealing with is the common log. The common log. I guess it's called a common log because it's used most often. But the base of a common log is 10 raised to some number. So you could do it all day long. You could enter any number, but we can represent any number by raising 10 to an exponent. Now it might be a big old exponent, but we can represent any number. Well, that exponent, we refer to that as the Bell. So what is the Bell of 10 to the 5.256? Well, it's 5.256 bells. What is the number raised to 5.25 bells? Well, what we find out is we use logarithms so often. When I come up here and look at my calculator, it might be the same key. It might be the same key, or it might be the same key shifted, right? It might be the same key shifted, or it might be a key right beside log. So here's log right here. What's right beside it? So yeah, so I can come over here and I can enter a number like 100, and I'm gonna hit the log of that, and it comes up and says 2, which is what 10 would be raised to. Well, if I wanted to find the number, I could just come over here and hit 10 to this, and it comes up and gives me 100. So look at your calculator. See, 10 to the x is going to be right there by the what? By the log key. So what was the number we have over here? 5.256. Well, all I have to do is I'll come up there and I'll enter 5.256, and I hit that key right there, and that's the actual number. Now look at that thing. So what exponents? We get into some engineering notation where, you know, I could hit 1/6, and I come up and I get a number that's unbelievable. So what do we start doing? We start rounding, right? You understand? We say in DC we want y'all to round to 2 digits. In this class, once you get it engineering notation, we want you to round it to 1 digit. But we got to round because we end a lot of numbers that comes up, and they either fall into a repeating number, or the fraction goes out so far it don't appear to ever start repeating, even though this one right here eventually would. That's the number. Y'all understand? And of course, if I hit the log key, it's going to come up and give me 5.526. So all the common log is it's a common base always of what? 10. So I can start representing things in bells, and now I can add exponents together, right? You understand? Because that's what we do. When we multiply numbers with exponents, and if they got the same base, all we have to do is just do what? Just add them together. But we need to round. And that's the number. Well, what will be the actual number for 2.4 bells? Well, I would just say what? You'll get the calculator, find that key. I would say what? 2.4, and then I hit 10 to the x, and that would be the number. 251 point big number. Are we okay? Everybody okay? I've got these on y'all's calculator. So that was the number I got. Huge number. Huge number. Relative to power, decibels, relative to power, decibels are equal to bells times 10. So how many dB would that right there be? 2.4. It'd be 24 dB. Because I can multiply by 10 just by doing what? Just shifting the fraction to the right. Huh? Go ahead. What do you mean? No, you're not logging. I gave you the log. I gave you the bells. And I'm asking for what number that represents. So you're going to raise 10 to this power. So what you're going to do, if I give you the bells, you don't take the log of the bells, because that's what the log is, right? You understand? So yeah, you're going to get a strange number if you do that. So if you got the bales, how do you convert it to the number? Well, I would enter the number. What was it? 2.4. And I'm going to raise 10 to that power. That's the number. You understand? If I hit log, we're going to go back to the original number. So this is bale. That we would say this is 2.4 bales. So that is the log, right? You understand of what number? It's the log of this number right here. But the problem is we need to come up with a method where I can round. We love rounding, right? So I need to come up with a method where I can round. Where's my PowerPoint at? Okay. I need to come, not that one. I must close that out, guys. I can't read those, they're too small. That's what I wanted. I need to come up with a method where I can round and still be fairly accurate. But you got to understand, us in approximations, we approximate all the time. Y'all understand? Because we do our math. Our math is perfect, but our components are not. So we do these calculations. Even when we did power supplies, you'd come up with these calculations and subtract this and do that. And then we made our measurements, and our measurements were never what we calculated, but they were what? They were close. That's what I like about that 0.9, where they did all the math. You can take your input RMS multiplied by 0.9, and you get a pretty good idea of what the output of your unregulated power supplies, unfiltered power supply is going to be. It's going to be a little higher than what you actually going to measure because they didn't consider what all the diode drops and all that other kind of stuff. So it says convert this to dB. All I do is multiply this number by 10, and I call it decibel or dB. So how many dBs would 2.4 bales be? Well, it would be 24 dB. Y'all understand that? You don't have to use a calculator. If you multiply by a number by 10, you just move it to the right. Now, I'm not gonna use that number to find I'm not gonna use 24 to find the actual number. In my head, I'm gonna shift it back to the what? To the left. But what dB is gonna get of it's just like you're saying, it's just like you say milli, but this is not near as accurate. All we're gonna do here is we're gonna limit the number of digits. Either we don't use any fractions, or we use one fraction, or we use two. I've never seen dB represented in more than two fractions. How many dB would that first one be? In your head, guys, what would that be? How many dB would that be? No, we're only going to move it over 1 decimal point. What would the first one be? 1.56, so it would be 122.3, the other would be 1.35, the other would be 58.56. Just move, we're doing it by 10. It's not engineer notation. All we're going to do, and we can do this in our head, we're just going to move it over to the right. How many decimal points? 1. Huh? I'm sorry, what did I say? 15.6, right? 122.3, 1.35, 58.56. Now you can't raise 10 to that number. But in your head, if you got dB, all you have to do is just shift it in your head back to the left and raise that up or guesstimate at it. We pretty much well know what 10 to the first is. What's 10 to the 0? Any number raised to the 0 power is, I don't care. Any number raised to the 0 power is 1. 0 is 0. 0 is nothing. We can't raise 0 to a power. Y'all understand that? So there's no such thing as raising something to a power and coming up with 0. So any number raised to the 0 power is 1. Do it. Make up a number. 55,536 raised to the 0 power, it's going to come up and say 1. Okay, y'all understand that? Okay, and then 10 to the first would be what? Raising 0 to a power. That's good. any 10 to the first would be what? 10. 10 to the second would be 100, 1,000, 10,000, 100,000. So if you came up and got, you know, a dB of 30 dB, then you know that would be 1,000. If it come up to be 30.4 dB, you know it's going to be somewhere between 1,000 and 10,000. So you can guesstimate that, right? You understand? It's going to be kind of off, but at least you know a ballpark of where it would be at. 56.6, 123.3, 135.1.35, and 58.56. Are we okay? And y'all thought dB was hard. Scientific calculators have a log key which converts numbers into bales. Once the number has been converted to bales, multiply the number by 10 to convert to dB. So what do we have to do? Just move the decimal where? Once to the right. The system has a gain of the following. 247, 576.34, 0.45, 0.67, and 0.07. Now what we've done right off the bat is I'm going to convert this to dB. Okay. So 29.93 dB, 23.92, 27.53, minus 5.65, 16.53, minus 1.74, and then minus 1.13. So if it comes up to be a minus, you know it's a gain of less than 1. Right? You understand that? If it comes up to be a positive number, you know the gain is greater than 1. So a negative means we have an attenuation, and a positive number, another number indicates we got a gain. Everybody understand that? Now, how could I do this? Well, what I'm going to do now is I'm just going to add these numbers together. Can you do that without a calculator? It'd be hard to multiply all these numbers, right? You understand? So could we do this? Sure. Calculating total gain. So I'm just going to add these. So this would be the long method. And it comes up and gives me a gain of 1,105,444.54. Now let's use dB. We just add them all together. Come up and get 60.444 dB. In my head, I'll shift it to the decimal to the left. I'll take 10 to that power, and that'll give me the gain. You understand? Okay. Yeah, just in your head. So you're going to raise 10 to the 6.044 power. It comes up and gives me a number that's a little different. Now, why is the number a little different? Well, let's see what happens. So let's look at the dB. So up here I said 647, 247 was a certain dB. But when I come over here and use my calculator and I say 247, and then I take the log of that, it's actually that number right there. So what did I do? Now, if I use that number right there and I raise 10 to that power, I come back and get the same number. But that would be a waste of time of using dB. Y'all understand? It's just like sometimes when you do your math, when you do your math on the electronic circuit, you come up with a fraction that's way out there. Well, what do? Well, you convert it to milli, right? So you can have whole numbers. And then what do? You drop a bunch of the fractions. Well, as soon as you drop fractions, then your answer is no longer totally correct. It's correct enough, but it's not totally correct. So what did I do with this number? What did I do with the number? Well, I moved it over. So let me get the number back up there. Sorry. So what did I do with the number? Well, instead of using, in fact, I rounded wrong. So it's 23.92. I'm sorry, it's right. So what I did is I moved it over. In fact, that 2 should have been a what? 3. So even I rounded wrong. And when I look at this dB right there, which was 567, if I come over and get, say, 567, I take the log of that, I come up with the same situation. So what are we going to do? Well, what we're going to do is we're going to start rounding these numbers. And this is where the system that they use, like I said, they either use whole numbers, they round to whole numbers, or they round to 1 fraction, or they round to 2. That's the most I've ever seen a dB round to is 2 digits. As soon as you round, and it's not going to be as accurate as we do. So when I say you use engineer notation and we talk about milli, I want you to convert it to milli and then round it to 1 digit. All we're doing here is moving it 1 decimal point. We're not moving it 3, right? You understand that? So that means the number's not going to be as accurate, but it's accurate enough. So I won't have to do all that math, right? You understand? So here all I have to do is just round, all I got to do is just convert it to dB. Of course here I rounded to, but this should be 3 right here. I converted these things over and rounded to 2 decimal points. Converted it to dB and rounded to 2 decimal points. But look how far we're off. So still it's what? It's close enough. Right? You understand that? Even though rounded, dB is still an accurate approximation of the actual power gain and is a heck of a lot easier to deal with than all that multiplication. Power is the rate work is being performed. Voltage is the difference in electrical potential caused by current flow. The main formula for calculating electrical power is power is equal to V times I. But remember that I is equal to V over R. So if I double the voltage to a circuit, what happens to the power in the circuit? If I double the voltage applied to a circuit, what happens to the power in the circuit? But tell me how much it goes up. You're exactly right, it goes up. How much does it go up? What do you think? Okay. If I double the voltage to a circuit, what happens to the power? Okay, what do you think, Kareem? If I double the voltage to a circuit, what happens to the power? If I double the voltage to a circuit, what happens to the power in that circuit? You should know right off the bat. What do you think, Courtney? What do you think, Brian? If I double the voltage to a circuit, what happens to the power in that circuit? Huh? How much? No, but if I double the voltage to a circuit, the circuit is set. So it is a circuit. I'm not changing any component in the circuit. All I'm doing is doubling the voltage to a circuit. What do you think, Charles? Okay, so y'all need to learn a lesson, and and you ought to know this, Courtney. You probably heard this 10 times in my classes. So let's say, but I is equal to V over R. I'm not changing the circuit. So let's say I come over here and I've got let's say a 1K ohm resistor. Okay, and then I come over here and I put 5 volts on that thing. Well, 5 volts, that's going to be 5 volts times 5 milliamps, and that's going to give me my power. Okay, now what I'm going to do is I'm not changing the circuit. I'm going to go to 10 volts. Well, if I go to 10 volts, there's 10 volts across that resistor. So now I've got 10 times 10 milli, and what happened to my power? Quadruples. It quadruples. So power in a circuit varies with the square of the voltage. If I drop down to 2.5, it drops down to 1/4. It don't double, it quadruples. Y'all understand that? Quadruples. And it varies with the square. If it goes up, it's the square. If it goes down, it's 1 over the square. Okay, y'all understand that? Because current and voltage are directly proportional. That's something you learned back in DC. Had all kind of questions. Voltage and current are directly proportional if the resistance don't change. So if you double the voltage to a circuit, the power quadruples. If you triple the voltage, it goes up 9 times. And of course, the story I tell, probably my mother called me and says, Rick, she called me Rick. She says, my electric stove won't even boil water anymore. And I went out there and she had lost one of her, up on the telephone poles, one of the lines had come loose. So instead of getting 240 volts on her element, she was only getting 120. And it wasn't even getting, so that was what, a quarter of the power she was getting up there instead of the full power. So we understand this now, right? Now in an amplifier, what gain am I looking for? Am I looking for a voltage gain or a current gain or a power gain? Killing me. Power is work, right? You understand? I don't go out there and say, okay, you're a big fella, I'm going to pay you a bunch of money. You go over and sit on your butt. You're not doing any what? You're not doing any work, right? You understand? Or you're out there like a chicken running around with their head cut off and you're not doing anything for me. You're still not doing work. So when you can have current, right, flow, and if you don't have, you got to have work is pushing against the force, right? You understand that? Force times distance, or here we use our force times speed, right? If voltage to a circuit, the current doubles and the power quadruples. And y'all, here's the answer to the question right there. Power varies by the square of the voltage. Voltage varies by the square root of the power. So if a current, and this is, so if a current has 10 volts at 10 amps, we'll get 100 watts, right? We double the voltage. What would happen? I'm tripling the voltage here. So that's why we want to really monitor that voltage. Now, that's why when y'all have something happen, where the voltage does go up for some reason, your light bulbs pop just like that. Just like that. That's why if you take a 120 volt bulb and put it in a 240 socket, it pops just like that. You take a 240 bulb and put it in a 120 volt socket, it's very dim. It very comes on and off. We do a thing in motor controls. We take a light bulb. We do it on purpose. We're simulating bad connections. So we're putting resistance in a circuit that's not supposed to have any in there. And we use light bulbs. And the way it calculates out, the light bulbs only have 30 volts across them. And people think the circuit's not working because the light bulbs don't light. But they're rated at 120 volts and we're only giving them 30 volts. Right? They're doing what work they're supposed to do, but they're not doing enough work to light up. Why ain't the light bulbs lighting? That's the one troubleshooting lab in motor control. In communication and power systems, we are very concerned about, with the amount of power produced or delivered. Power gain and loss is very difficult to measure because it's voltage times current. Voltage gain and loss is very easy to measure. So the way we would do power gain, AP in dB. Now dB is not a unit. You understand? That would be just like me saying milli or micro. Micro is not a unit. It's not volts. It's not amps. So dB is not a unit. It's just a method that we can represent large numbers with few digits. And plus it sounds good. You start talking about dB and people think you're smart. So power gain, the formula is in dB would be log P out over P in. And my answer would be in dB. Now, most calculators, this is the formula, but just about all calculators, you have to work it backwards. Notice you got what we call a reverse Polish calculator, where you actually put the equation in there. Standard entry calculators, we have to work from the parentheses back, right? You understand that? Anybody that has algebra knows that. So what we would do here is we would measure the power, power out over the power in, then whatever number we get, we take the log of that number, and then we multiply it by 10. I'm sorry, that's not the formula. AP is equal to log 10 P out over P in. Now, what's the problem with measuring power gain? How would we measure a power gain? How would we measure? But how would we measure it with a meter? All we got is, Well, we're going to have to know two things, right? What are we going to have to know? We're going to have to know the voltage and the current. So when I take my without doing calculations, right? Understand. Well, what we have to understand, I know if I've got a resistor and it's a series resistor, I know I can measure the voltage drop across it and calculate the current, and use the calculated current to calculate the power. And we've been doing that a lot this class, right? Using that, finding a series resistor and calculating what voltage we expect to get a certain current, or we've been measuring it and using that to calculate it. What we're doing here is we're dealing with dB. Are we okay? I understand. So it would be real easy for me to measure voltage. I could take my voltage, I could take my scope and put it on the input, I could take a scope and put it on the output, and I could very easily see my voltage now. So I could take V out over V in. But what's voltage relative to power? Varies with the what? So power varies with the square of the voltage. Y'all understand that? The square of the voltage. Now, if I have 10 to the first, and I multiply it by 2, that would be 10 to the second. And 10 to the second is 100. Well, 10 squared is 100. If I took 10 to the second and multiply it by 20, that's going to be 10 to the fourth, which is 10,000, which is the same as 100 squared. I understand. Power varies with the square of the voltage. So if I can measure the voltage, I can calculate the power gain by using voltage, by using another little formula. Oh, this is the power. Okay. 10 amp, 600 watt problems. Okay. So voltage varies by the square root of the power. Voltage varies by the square of the power, by the square root. So let me get to the actual formula. Okay. So power is AP is equal to 10 log. Sorry, 10 log P out over P in. or 20 log V out over V in. Of course, we could do I out, but we very seldom use that. Do you understand where the 20 came from? It's square. That's right. That's what it is. It's dV. So to go to dV on power, we multiply it by 10. But if it's voltage, I multiply it by 20. And you get exactly the same power. You calculate power gain, but how you calculate it? You're calculating it by voltage, right? Y'all understand that? Yes or no? So here's our formula for dV. Okay, so let's talk about bandwidth. Anybody know what bandwidth is? So the book's got a pretty good picture on page 245. So what happens most of the time is we'll start off running through an amplifier. And then what happens, we'll start raising the frequency. And what usually happens, and this is not always true, is that we'll come up here and a media would come up and give us something like that. It would come over here, and this is frequency. And then this right here is volts. And what happens, it'll start having an output, and then eventually my output will start rising, and then it'll level off, and it'll hit a maximum value for a while, and then the frequency still going up, and then things start happening, and then the output will start dropping down. Now this is pretty, but it's usually a little different from this, but it's close. And we're not going to get in how you can calculate the bandwidth of a transistor. They got something called the bandwidth product. So what I'm going to do is I'm going to slant this a little more so we can see this. Now this is volts. Now the bandwidth is defined as the half power point. So if I was to come up here and start drawing this with power, then right about here, this would be when the power gets above 50% of the maximum value. And this is where it drops down to 50% of the maximum value. So this would be max power that I get out of my system. Now follow this so far. So bandwidth is, we call this guy right here, this is called F1. This is called F2. And then bandwidth would be equal to F2 minus F1. Now that's the way we would measure it. There's different ways we calculate it. So measuring is one thing, but you need to know what you get before you go there. And we're not going to get into how to calculate bandwidth. This is the way we would measure it. So I'd hook up an oscilloscope to it. I start at a real low frequency. I keep my input the same voltage, and sooner or later you'd see it go up. And then what would it do? Then it would drop down. So when I look at my oscilloscopes, sometimes the bandwidth looks like this. So an oscilloscope has a bandwidth rate an oscilloscope has a bandwidth like this. So it'll measure DC. Oscilloscope measures no frequency. So it has a bandwidth of 0. And then, so its bandwidth would be whatever the upper limit is. So when you look at your oscilloscope sometime, look up at the corner, it says 25 megahertz. Well, that's the bandwidth for that scope. So that means that scope guarantees that if you get up to 25 megahertz, what you're seeing is probably going to be half power of what you actually measure. The problem is your oscilloscope is not measuring power, it's measuring what? Voltage. So how would I relate this to voltage? So what would be the half power point of, what would be voltage if I wanted to see the half power point? What voltage would I measure? I'm not going to measure half voltage because power varies with the square of the voltage. Yeah, but I'm measuring a voltage level. So I got my scope hooked up there, and I'm trying to measure the bandwidth. So I'm looking at voltage. I'm not looking at power, but bandwidth is when the power drops down below 50% of maximum power. So how would we do that? Well, I'm not going to show you. It takes a little, it's not, we'll just show y'all. Let's say I start off, I've got, this would be my maximum power. So power, let's say I got 10 volts and I got 10 amps. So what would be my power? Be 100 watts, right? Now, of course, if I have my voltage, it's going to go down to 25 watts. But what we're looking for is we're looking for 50 watts. So the magic number, guys, is 70 point, it's actually a bigger number. It's 70.7%. So let's do that. So let's say power, I'm going to decrease this by 7, so it'll go down to 7.07. If my voltage goes down to 7.07, then my current's going to go back to 7.07. And what's that power? It's going to be 49.9. What's that? That's 50 watts. We're rounding, right? You understand? It's actually the reciprocal of square root of 2. We say 0.707, but you see we use that a lot. So if I can measure my voltage, and then when it gets up here, first of all, I'll find the maximum voltage. And once I find the maximum voltage, I'll start dropping the frequency down. And when it drops down to 7.7%, I would call this what? I would call this F1. And when it drops down to 70.7% right here, I would call this F2. And we'll do this with an amplifier. You can actually see the bandwidth of an amplifier. So one of the things they give you when you buy radios and stuff like that, if you look at the technical data, they give you the bandwidth. And this is the range of frequencies it can reliably pass and still maintain at least 50% of the maximum output power. Now, let's say I have 100 watts. Let's see if this is going to work out. Where's my lock key? Where's your lock key on this, Rich? Okay. So let's say I start off with 100 watts. Then that means half power would be 50 watts. So I'm going to say 50 divided by 100. So this is my out. This is my in. And it's going to come up and give me what? 0.5. Right? You understand? Then I'm going to take the log of that, and it comes up and gives me minus 3 dB. And let's say I have 100 volts, and it drops down to 70.7 volts. So it's going to be 70 0.7 divided by 100. And then I'm going to take the log of that, and then I'm going to multiply that times 20. And it comes up and gives me minus 3 dB. Understand what I just did? Okay, so let's do the log of this. So I'm going to come up here, and you can make up any number because it's a half power point. So what I'm going to do is I'm going to come over here and I'm going to say, okay, I get 50 watts. So half power, if it's 100 watts maximum, half power would be 50 watts. So I'm going to say 50 out over N, that would be 100. That gives me 0.5. Right, you understand? Then I take the log of that, it's going to be 0.3 something. Then I convert that to 3 dB, and it's going to be a minus 3, it's a minus 3 dB. Everybody okay? Is that okay? All right. So let's do it over here with voltage. So here I'm starting off, I've got 70.7, that's my half power point. I'm putting this 100. Now that's 0.707. All right, you understand that? Are we okay? So I'm sorry. Take the log of that, right? No. Okay, take the log of that, I get a minus 1.5. I'm sorry, I get a minus 0.15. Then I multiply that times 20 because it's voltage, and it comes up and says minus 3 dB. So we just said, okay, if I take a dB over on the power, and instead of using power, I use voltage, but instead of using 10 log, I use 20 log. We come up and get we get our power gain or our power loss. So you'll see people. So bandwidth, we can say it's 50% of the power. We can say it's 70.7% of the voltage, or minus 3 dB. So bandwidth is measured at minus 3 dB. Is that power or voltage? It's both. But actually it's power, right? You understand that? So that's for the minus 3 dB. So what do we use dB for, guys? You're going to run into dB, but now you got a little feel of what dB is, right? You understand? It's a method of measuring gains and losses, but we, instead of using the numbers, we use 10 as the base, and we use exponents. And what's nice about using exponents, if the base is the same, how do you multiply exponents? You just add them together. And then to find what it is, to get that in dB, we would just shift the decimal point over to the right. We call it dB. And then we're going to round it. You can round it to whole numbers. They use whole numbers a lot. And anytime they use whole numbers, they're definitely an approximation, right? You understand? You could round it to 1 decimal point, or you could round it to 2. And that's the most, like I said, that's the most I've ever seen. And of course, when you convert it back, in your head, you move it to the right one time and then raise 10 to that power, and that'll give you the approximate gain in power. So all those gains we gave you was power gains. But the problem is, well, they could have been voltage gains, but if they were voltage gains, to find the approximate power gain, we would use what? 20 log V out over V in. So that way we can measure voltages and get a good idea of what the power gain is. Okay, I'll take a break.